So this is about possibly paraconsistent sets, and the whole video is based on our own concepts and they have not been published yet. So the idea is to propose a kind of new semantics for tripartite division of the initial non-empty universe. So the whole approach is connected with free-valued logic of Łukasiewicz, but also with Choker's intuitionistic sets and so-called double, or if you prefer, flow or maybe weak rough sets. In fact, this semantics is isomorphic with them. But on the level of meaning, of semantics, of applications, this approach is slightly different and covers different problems because we define a possibly paraconsistent set on some non-empty universe X as an ordered pair of the form A and then tilde A or sim A, because we used sim command in LaTeX, with the assumption that the whole complement, classical complement of A, is contained in sim A. So sim A is bigger than, maybe it's bigger than the complement of A. An example is here. Yes, here you have three possible paraconsistent sets on this universe X, A, B, and then C, but C is also an intuitionistic set. Yes, in this particular case, sim A is identical with the complement of A. Then we define several algebraic operations in this framework. For example, we have union, so we add those A and B components and we intersect sim components. Then we have strong union, we add everything. Then we have intersection, so we have intersection here, intersection of left components and the union of the right components. Then we have restricted strong intersection. It's something like strong union, but due to the fact that this operation should return possibly paraconsistent set 2, it is modified here on the right side. So we have intersection, but with the union of the complement of A and B. And then we have complement. AC is just like sim A. You see that those operations are similar to those that, in particular union and intersection, are similar to those that are used in the setting of intuitionistic sets. The same can be said about distinguished sets tilde empty and tilde X that play the role of the empty set and the whole universe. Contrary to the situation in intuitionistic sets, where you can define empty pair, here you can define XX pair. As for the inclusion, it's depicted here. It's just like in intuitionistic sets. I mean that the first left component should be contained in the second left component, and we have reverse situation in case of the right components. And this preorder is induced by both union and intersection if they play the role of addition and multiplication in the sense of lattice. And if we have this algebra, X union intersection complement with tilde empty set and tilde universe, then we may prove that the whole framework is just a De Morgan algebra. So we have commutativity, idempotence, De Morgan laws, distributive laws. Well, they were not mentioned here, but we have absorption laws too, okay? A double negation and those properties that are also typical for any De Morgan algebra, but not necessarily the law of the excluded middle and not necessarily the law of contradiction, of non-contradiction. Alternatively, we can use this algebra with lower length, so strong union, strong intersection operations. What is important that in this case we have only one absorption law, which is here. We have, as you can see, we have associativity. One can prove that there is no distributivity of these operators, but what is important is that we have only one absorption law. This is written here, and for the second absorption law we have, for example, this this proof, this counterexample that tells us that this absorption law, that A lower A land B is A, that this doesn't hold. The set, the resulting set, is different than A. So we see that our structure of possibly paraconsistent sets with these two operations forms so-called bisemi-lattice with only one absorption law. Such structures were mentioned by several Polish authors in 80s and 90s and analyzed from the purely algebraic point of view. Besides, we can prove several other identities here, as you can see. One can prove that the setting of possibly paraconsistent sets with standard union, intersection, and complement is isomorphic with the structure of Choker's intuitionistic sets, so-called orthopairs, with analogous operations. These operations in intuitionistic sets are just like, one could say, just like in possibly paraconsistent sets, but with the assumption that the first and the second component have empty intersection, like here, okay? Because this is the idea of Choker's intuitionistic set. Then we have several technical points, like by induction, we want to understand, to use the symbol of, possibly paraconsistent set with tilde on the right side. So it's here, these definitions are taken just from the definition of algebraic operators, and using this we can define white hat A, which is the set of those elements of our universe that are exactly in A and are not in the complement of A nor in the mutual part of A and sim A. So it's exactly this, okay? Those elements that are, one could say, that are only in A. One can prove that the following identities hold, that white hat of A intersection B is like intersection of white hats of A and B, the same with union, and something similar with complement. We omit proofs as always, and then we can use the following function. If we have a possibly paraconsistent set A, then we can compare, connect, and assign to it the following intuitionistic set: white hat A and the complement of A. White hat A refers, here we use the font for possibly paraconsistent sets because the exact shape of white hat A relies on the shape of sim A. Yes, so it refers maybe not to the classical A, but to the whole possibly paraconsistent set. But be as it may, this is an intuitionistic set, of course. These two components have empty intersection. And then one can prove that this function is one-to-one and surjective, and it's a homomorphism between the setting of possibly paraconsistent sets and the setting of Choker's intuitionistic sets. Then we have a similar function, like here, white hat A and the whole A. So this gives us an analogous relationship with weak graph, or if you prefer, double or flou sets, which are nested, yes? The idea of a weak graph set is that you have A1 and A2 with the assumption that A1 is contained in A2, and you have union defined in a very standard manner and intersection defined as here, okay? But we can analyze this algebra again, and you can define two appropriate operations in the framework of weak graph sets. As you can see, here you have intersection and union. Here you have union and intersection of those external union union intersected with the intersection of those external components, and then the second element is the intersection of those external possibility components. This is in the setting of weak graph sets. In fact, we analyzed these two operations under the name of negotiation sets a few years ago, as far as I remember. And then you can show that our function g becomes an isomorphism between bisemi-lattice of possibly paraconsistent sets and bisemi-lattice of those weak graph sets with these two operations. That's all for today. Here you have some kind of bibliography about intuitionistic fuzzy sets, intuitionistic sets, neutrosophic crisp sets, because one can check that our possibly paraconsistent sets can be considered as neutrosophic crisp sets of type 2 also, and something about soft double sets and weak rough numbers and weak rough sets here. Thank you very much for your attention.